Hello everyone. In this video, we will review some of the basics from chemistry. These will be important to get us started in this course. So we will get to remind you of the basic picture of the electronic uh, structure of an atom. So there is this, let's take a simple atom and try to discuss it. For example, the magnesium atom. There are 12 electrons in this atom. And there is this simple model that we can think of where there is a nucleus, a positive nucleus, and then there are the energy levels where the electrons can live. So if you think of this simplified picture, in the first energy level, you might have two electrons. In the next energy level, you need to fill in with 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. And eventually you are left with only 2 electrons, and those will exist in the outer level. The typical terminology in chemistry that these electrons close to the nucleus are called the core electrons, usually not very important for chemical reactions. And we will discuss this later, especially when we talk about density functional theory. And then there are these outer electrons where we usually call them the valence electrons, and these are known to participate in chemical reactions. So that's really the simple picture uh, of of the electronic structure of an atom. But then, when you have different atoms or even similar atoms coming together to form either a crystal or a molecule, then you start forming what's known as bonding. Um, Bonding is a broad term. We might consider it as either chemical bonding associated with charge transfer, so electrons moving from some place to another, or much simpler physical bonding or weaker bonding, which is usually we term it physical, similar to van der Waals interaction, which is, a weak interaction, but still very important. It's not associated with charge transfer. And there is this classification of bonding, which we will follow here. Um, we will talk about metallic bonding. Um, there is also covalent bonding, right? There is ionic bonding. And then these usually people term as the primary types of bonding. And then there is a secondary type of bonding. Although the name secondary gives you the impression it's less important, but it is really very important, which is van der Waals interaction, or van der Waals bonding, if you want to call it bonding. So we will briefly go over the simple picture of these types of bonding. So let's actually get started with metallic bonding. So the first is metallic bonding. If you think about what kind of elements form metallic bonds, so immediately you would go to something like iron, maybe cobalt, nickel, sodium, and so on and so forth. In fact, there are even some compounds that exhibit metallic bonding. For example, some metal oxides that are behaving as metals. But again, we will leave the discussion of these exotic materials to later parts of the course. But so these are the kind of elements that you can think of forming metals. If you think about sodium, it has 11 electrons, and just like again, we can cast its electronic structure in very simple picture. There is the 1s orbital with 2 electrons. There is the 2s orbital again with 2 electrons, and then there is the 2p. And let's see, there is 1, 2, 3, 4, 5, 6. So in totality, now we have 10 electrons. So this is 2p. And then finally, in the 3s, there is our lone electron. And if sodium loses this electron, it will be happy. It will be forming a closed shell structure, and it will be happy. And this actually what happens in a crystal of sodium. So sodium would crystallize tentatively into BCC crystal structure We are not. We'll discuss later why I'm saying tentatively, because there are these questions about the crystal structure at which temperature. But let's say commonly it's known that sodium crystallizes in the BCC crystal structure. And if you look briefly on how these sodium atoms will arrange themselves in this crystal, in this very simplified picture, you will have sodium plus ions, right? Where each one of these sodium atoms lost an electron. So you'll have Na plus ions sitting in crystalline sites, and then you have a sea of electrons that's floating around, that's surrounding these ions. So this sea of electrons is made. Maybe let's make this better. So this sea of electrons is made out of the one electron that each one of these atoms have lost. So it's a sea, and it's really not possible to distinguish which electron belongs to which atom. So it's like all of them cooperatively are participating in this type of bonding. Uh, so this, let's call this sea of electrons. And because of this cooperation among these atoms, metals are known to exhibit what is known as many-body effects. Yeah, strong many-body effects, in fact. The reason for this is that the sea of electrons which glue together these positive ions have been created or has been created by the participation of each one of these ions. So this is really the simple picture of the metals. Now let's move on to another type of bonding, which is covalent bonding. You would think of covalent bonding taking place, if you think in terms of crystals, you would imagine something like silicon forms covalent bonding, carbon forms covalent bonding. What else? Small molecules, like the hydrogen molecule, for example, or maybe H2O molecule. The primary backbone of proteins, for example, this is also is made out of covalent bonding, so backbone of proteins. And there are many places where you find this covalent bonding. So it's a very important type of bonding. So let's see how it is actually made. So in covalent bonding, the um, the stability of the atoms is reached by sharing electrons. So the key idea here is sharing electrons. Let's take a very, very simple example. Suppose you have one hydrogen atom surrounded by one electron and another hydrogen atom surrounded by another electron. Then the stability can be formed by creating the hydrogen molecule, where these two electrons are shared among the two atoms. In species that have a larger number of electrons, the stability is happening when the outer electron is filled by eight electron shell is filled by 8 electrons. So, for example, think about silicon. Um, so this is another example here. If you take silicon in its crystal, you can imagine silicon atoms, each one of them is having 4 outer electrons. I'm depicting here uh, part of the crystal. So, and if you focus on this central atom, so it has 4 outer electrons. You can actually show this by looking at the electronic structure of the silicon atom. But then the other atoms, each one of them will share an electron with that central atom. So this belongs to this silicon atom, this belongs to this belongs to this, and this belongs to this. So in totality now, the central atom is feeling stable by having these 8 outer electrons. Remember that this structure is extended. So again, there is another silicon here, and another silicon here, and another silicon here, and you can think of this also as a central atom. It's sharing 2 electrons. It's sharing its 4 electrons, and it's happy with the outer 8 electrons that it currently it currently have. So you see, stability here is done by sharing electrons. The electrons, they have some location in the space in between these two atoms. Another feature of covalent bonding is that it leads to some characteristic angles. So it leads to some characteristic angles, and that's what's known in literature as three-body effect. So three-body effect. For example, in silicon, if you take in the silicon crystal, which might have a chance to look at it later, if you take three silicon atoms, they typically form an angle of 109 degrees in a space. This is the famous tetrahedral angle. So covalent bonding is always associated with this kind of three-body effect in a space. Another example, which might actually set in another page here, which we might set in another page here, is the water molecule. So the water molecule, if you think about it, there is also the oxygen atom and then hydrogen atoms here. There is some covalent bond here formed, and then the oxygen has its these lone pairs of electrons, but then there is this covalent bonds with hydrogen. Again, the hydrogen bonding is leading to a characteristic angle here, which is 104.5 for liquid state water. So in general, um, covalent bonding is associated with angles, and that's why people always talk about three-body effects when it comes to discussing covalent bonding. So this completes the discussion of the covalent bond. Now let's move on to the next type of bonding in another page. So next we have um, the ionic bonding. And you can think of ceramics, what people call ceramics, as a classic example of ionic bonding. For example, something like magnesium oxide, something like the salt, the table salt, NaCl. And the key idea in ionic bonding here is that there is more or less a complete charge transfer between one species to the other. So here, electron is transferred almost completely. Almost completely. I'm saying almost because there is in the quantum mechanical picture, there is no room for a naive image of an electron as a dot moving from one species to another. So it's transferred almost completely from the cation to the anion, from the cation to the anion. So think of uh, maybe magnesium oxide as an example. Magnesium, if we go back, actually, it's when we started this discussion, let me go back. Magnesium has two electrons in the outer shell, and it would love to lose them. So if we think of a magnesium oxide crystal, something like this. So I have one magnesium ion here and another magnesium, and then maybe another magnesium and then another magnesium. And then we have oxygen. So there is an oxygen here, an oxygen here, another one here, another one here, and so on and so forth. So you can think of all these magnesia atoms became ions. They became cations by losing two electrons. So I have Mg plus 2, Mg plus 2, Mg plus 2, and so on and so forth. And the oxygen atoms, they become anions, so they become an oxide ion upon receiving these two extra electrons. Definitely, this is a simplified picture, but it serves the purpose. Now, expressing the interaction between these anions and cations is very straightforward, because you can think of a simple Coulomb law. If you go back to your basic physics studies, This is the Coulombic force here is 1 over 4 by epsilon naught epsilon r. Epsilon r is the relative permittivity and epsilon naught is the vacuum permittivity. First charge, second charge divided by the square of the distance. So that's the force between two ions. We haven't discussed what kind of forces exist in a metallic bonding or in a covalent bonding because it's not straightforward to describe these. We will see how people try to model them in subsequent videos. But for now, we will really just take the simple picture that how is the bond is formed. I have something else to say that none of these bonding types that we discussed is pure. In what do I mean? I mean that there is nothing where I can call this material is purely ionic or purely covalent or purely metallic. There is always a mixed character. And people have tried along the literature trying to find ways to characterize how much covalent this interaction is or ionic. But you know, there is no fundamental law of nature that can actually tells you about the nature of this interaction. Okay, the last and not definitely not the least is van der Waals. So van der Waals bonding. It's kind of covalent bond. Sorry, it's kind of physical bonding because there is no charge transfer, there is no electron transfer from a species to another, and it exists everywhere. It exists everywhere. This kind of bonding is everywhere. In particular, certain species that predominantly exhibit van der Waals interaction are noble gas crystals. So, for example, if you have a crystal made of neon or argon, then these crystals they usually crystallize in the face-centered crystal structure, something we will have a look at later. So when they become solids, the dominant interaction in these solids is the van der Waals interaction. But it's not only in these noble gases, it is actually a generic interaction. It exists everywhere. As I said, if we are talking about a metal, let's actually go back a little bit. If we are talking about a metal, then there is still some van der Waal among these ions. If you are talking about silicon, hydrogen, or any covalently bonded system, there is still some van der Waals there. Similarly, in ionic materials, it's never a pure Coulombic interaction. There must be some van der Waal into the picture. So what is the origin of van der Waal? The origin is very straightforward. Suppose you have two neutral atoms. Let's think of, let's say two argon atoms. So maybe one argon atom here, there is this nucleus, and this is this nucleus, it's argon and argon. And you can think of the electronic cloud as spherically symmetric. So because of the spherical symmetry, what's happening here is that this is completely neutral. So the charge here is zero, and the charge here is zero. So there is no interaction. But then it turns out that at some instant of time, this spherical shape of the charge density, maybe because of some atomic vibrations, can get polarized. Polarized in the sense, so let's draw another picture. Polarized in the sense that the nucleus maybe with a little bit of electrons get somewhere while the rest of the electrons go to another way. So they form this ellipsoidal shape where part of the electronic cloud becomes positive now because of the existence of the nucleus, and the other part becomes negative. But this instantaneous picture, definitely there is a dipole moment here. There is an electric dipole moment. It induces another similar moment on the other atom. So it also polarizes and it takes this ellipsoidal shape or close to ellipsoidal shape. And then because of this dipoles getting to or arranged together, you end up with attraction between them. Attraction between them. This attraction is what leads to van der Waals attraction. This is what's known in literature as van der Waals attraction. So it is really a dipole. If you think about it, it's dipole, dipole, interaction due to polarization of the electronic clouds, And as I said, this exists everywhere. I have to say something on top of that, because this is really a matter of convention. How would you like to describe this? Some people also talk about another component of van der Waals that appears at short distances. So let's actually open another page here. So previous van der Waals, let me give van der Waals this acronym. Previous van der Waals attraction appears at long distances, or not necessarily appears, let's actually say dominates, at long distances. At very short distances, the electron clouds overlap, which causes huge repulsion, We will get to this picture again. That huge repulsion, some people would like to classify it as a still van der Waals. That's actually very common, for example, in many software packages to talk about this short distance repulsion as a still van der Waals. And some people call it a special type of interaction, maybe exchange interaction, as in the language of quantum mechanics and density functional theory. But we present it here among the discussion of van der Waals because, as I said, it's still actually common in literature to see this. So let's actually go back and recap very quickly. We discussed the electronic structure of an atom briefly in a very simplified picture. The dominant types of bonding are metallic, covalent, ionic, and there is a secondary type of bonding that's mainly physical, which is van der Waals. So the picture in metals is that atoms lose electrons, forming a sea of electrons that glue these metallic crystals together. And there is definitely a strong many-body effect taking place. The second interaction is covalent. Covalent is by sharing electrons to reach stability, and it leads to some characteristic angles like the tetrahedral angle in silicon, and this is also known as three-body effects. The third type of interaction is ionic bonding, and there is sort of a complete charge transfer between one species to another. This leads to an arrangement of cations and anions. Remember, positive cations, negative anions. And usually the interaction between them is easy to represent using Coulomb law. And finally, van der Waals interactions. It's really a dipole-dipole interaction at long distances, which leads to attraction. It exists everywhere. However, at very, very short distances, because of the overlap of the electronic clouds, again, maybe I should draw a simplified picture here. Again, take these two argon atoms getting really closer to each other, and then this overlap between electronic clouds will lead to a huge repulsion at short distances. Thank you, and see you in another video.